From the very moment the cosmos came into being, every aspect of our existence, every step we take, every thought we form, every breath we draw, has depended on a colossal nuclear reactor shining in our sky, the sun. It's a concept as awe-inspiring as it is humbling. We are more intimately connected to that distant star than we often realize. As the astronomer Carl Sagan famously said, "The cosmos is within us. We are made of star stuff." Consider the carbon atoms that form the cells in your body. They were forged long ago in the hearts of stars. During the Big Bang, only hydrogen, helium, and a little lithium were present. Everything else, carbon, oxygen, iron, the elements that make life possible, was cooked up in countless stellar furnaces. Your body's atoms likely come from many different stars, mixed and merged through billions of years of cosmic evolution. It's a staggering thought. You carry within you a legacy of ancient, long-dead suns that breathed life into the universe's chemical tapestry. Some people may ask, isn't there more meaning to it all? But what could be more meaningful than understanding that the very fabric of your being was assembled over eons by the creative processes of the universe? The atoms that compose you formed spontaneously into temporary structures, cells, tissues, organs, that think, feel, and ponder their origins. In time, these structures will break down, and in the far future, no complex structure may remain. Yet for this brief window, we gaze at the cosmos and comprehend our place within it. That perspective, that journey to understand and accept our cosmic heritage, is the true treasure. Shying away from the immensity of time and space and the profound revelations of science means missing out on one of life's greatest joys. Compared to the sun, our lifespans are fleeting, mere instants against its seemingly timeless glow. But the sun, too, is not eternal. Like all stars, it has a life cycle. Stars form, they shine for millions, billions, or even trillions of years depending on their mass, and eventually they die. Their fates are determined by how heavy they are. All stars, including our sun, begin their journey as clouds of gas and dust, nebulae, or molecular clouds. Over millions of years, these clouds collapse under gravity, growing denser and hotter until they ignite nuclear fusion in their cores. At this point, a protostar becomes a main sequence star, a stable phase that, for about 90% of stars in the universe, lasts the majority of their lifetimes. Our sun is currently in this main sequence stage, converting hydrogen into helium through nuclear fusion at its core. Unlike burning wood or paper, the sun does not burn in the way we usually imagine. Instead, its immense energy comes from fusing hydrogen nuclei into helium. Every second, the sun fuses about 600 million tons of hydrogen, releasing an incredible amount of energy. At this rate, it has about another 4 to 5 billion years before it runs out of its core hydrogen fuel. Scientists have confirmed this by studying how the sun vibrates, its internal ringing revealed by a technique known as helioseismology. These subtle oscillations let us peer inside the sun, confirming its composition and how much fuel remains. As a star consumes its fuel, its internal balance shifts. For stars like the sun, once most of the hydrogen in the core is used up, fusion moves into surrounding shells and the star begins to expand, becoming a red giant. In billions of years, the sun will swell, likely engulfing Earth and any life that may still exist here. When a star of the sun's mass finally runs out of fusible material, its outer layers drift away as a beautiful planetary nebula, leaving behind a dense core known as a white dwarf. Held up by quantum rules that forbid electrons from being squeezed too close together, a white dwarf is roughly the size of Earth but incredibly dense, packing the mass of a star into a volume millions of times smaller. More massive stars follow more dramatic paths. They can fuse heavier and heavier elements in a series of concentric shells around their core. Eventually, they produce iron, the cosmic dead end of fusion. No energy can be gained from fusing iron, so when a star's core becomes iron-rich, it can't hold back gravity anymore. In a violent instant, the star's core collapses, triggering a supernova explosion that blasts its outer layers into space. What's left behind can be a neutron star, a city-sized sphere of neutrons so dense that a teaspoon of its matter would outweigh a mountain. Or, in the case of even more massive stars, a black hole. Neutron stars are held up by neutron degeneracy pressure, a quantum mechanical effect similar to what holds up white dwarfs, but even more extreme. A typical neutron star might contain 1.5 times the Sun's mass, packed into a sphere only about 10 miles across. If the star is too massive, not even this pressure can halt the collapse, and the core shrinks until it forms a black hole, a region of space so tightly curved that not even light can escape from inside its boundary, known as the event horizon. Some of the most energetic events in the universe come from these stellar deaths. When a massive star collapses, a supernova can occur. In even rarer, more extreme cases, hypernovae, the explosion is even more energetic, possibly accompanied by long-duration gamma-ray bursts, GRBs. These are some of the most powerful blasts known, visible across billions of light-years, and they are key to understanding the most extreme physics the universe has to offer. If hypothetically, a gamma-ray burst occurred close enough and pointed directly at Earth, it could have devastating consequences for life here. Thankfully, all known GRBs have come from distant galaxies far beyond the Milky Way. Among these bizarre stellar remnants, we find pulsars, rapidly rotating, highly magnetized neutron stars that beam radiation from their poles, sweeping their lighthouse-like beams across the cosmos. When pulsars were first discovered, their regular pulses were so precise that scientists jokingly named the first one LGM-1 for little green men, wondering if these signals could be from alien civilizations. Instead, they turned out to be entirely natural beacons of astrophysical wonders. Observations of pulsars have even helped confirm the existence of gravitational waves and aided in discovering the first exoplanets. And then there are the black holes, the darkest mysteries of them all. We cannot see them directly, but we can detect their influence. They can roam interstellar space as rogue black holes, formed when galaxies collide and their central black holes merge or get flung out into the darkness. Our own galaxy may harbor many such solitary black holes, invisible except for the gravitational lensing they produce, or their effect on nearby stars. In recent years, gravitational wave observatories like LIGO, Laser Interferometer, Gravitational Wave Observatory, have opened an entirely new window on the cosmos. They have detected the echoes of black hole mergers, events where two massive black holes spiral into each other at incredible speeds, releasing more energy in a fraction of a second than all the stars in the visible universe combined. These gravitational waves, rippling through the fabric of space-time, confirm that black holes are not just theoretical oddities, but real and dynamic actors in the grand cosmic drama. We have also seen neutron stars crash into each other, producing gravitational waves and forging heavy elements, like gold and platinum, that sprinkle through the universe. Each gravitational wave detection and each new observation of stellar death and rebirth deepens our understanding of these distant realms, from the nuclear furnaces of stars that forged the atoms in our bodies, to the violent deaths that scatter enriched matter into space, to the compact remnants, white dwarfs, neutron stars, black holes, that follow. The universe's cycle of creation and destruction is intimately linked to our own existence. By observing these cosmic phenomena, we connect the dots of our cosmic origin story. The fact that we can measure, predict, and understand events so far beyond our daily experience is a testament to the power of human curiosity and intellect. In facing the incomprehensible scales of time and space, and the mind-bending processes that shape galaxies and star systems, we learn not to diminish ourselves, but to enlarge our perspective. We discover that the simple fact of our existence, composed of star-forged atoms and capable of understanding these cosmic truths, is one of the greatest wonders of all.